Next, let's talk about some properties of continuous functions. So remember we talked quite a bit about taking two functions and making a new one, and we had these standard ways of combining functions. In addition, we also had the limit laws, which showed that you can pull through the limit, you can pull the limit through for all of these. So using those limit laws is having proved the limit laws, by the way, which, okay, we didn't do it, but if you go in the extra materials, you will see there are some proofs there if you're interested. Having proved the limit laws, we get these for free, okay, because of our definition, which involves the limit. So what we're saying here is that if f and g are continuous at a point A, right, because remember continuity is defined at a point, then, and of course c here is a constant, then all of these functions are also continuous at the point. The sum, the difference, multiply by a constant, multiply the functions, or divide the functions as long as I'm not dividing by 0. So that's very nice. And again, we pretty much get those for free from the limit laws. And what it tells us immediately is if we apply this to the right functions, namely monomials, or the function y equals x even, and just keep doing it, we know that therefore, that would tell us that polynomials are continuous everywhere. So that's what I'm going to write down. So polynomials are continuous everywhere because their domain is everywhere, right? The domain is minus infinity to infinity. Rational functions are continuous everywhere as long as you don't have an asymptote, right? As long as you're not dividing by 0. Of course, if you're dividing by 0, it's not on the domain, right? So what we can say is we can say the following functions are continuous everywhere on their domains. So polynomials, which are continuous everywhere because their domain is all real numbers. Polynomials, because spelling is important. Rational functions. So where it's not going to be continuous, you're going to 0 in the bottom. Most likely it's going to be a vertical asymptote, but sometimes you'll have that 0 over 0 deal where you have a hole, like we've seen. Now, but we also know a lot of other functions, and most of the functions that we know are continuous, right? So, for example, trigonometric functions now, to prove that trigonometric functions are continuous, you do have to do a little bit of work. But for now, we can just sort of say, let's think about sine and cosine. The graph is continuous. You're going all the way around the circle. If you think about those as being defined around the circle, that's going to be continuous. And in fact, when you get to the endpoint all the way around the circle, you are going to see that that it meets up. So you can show that for sine and cosine, and then tangent is just sine over cosine. The asymptotes, of course, are not in the domain. So everywhere besides those vertical asymptotes, your tangent function is going to be continuous. So on each piece, on each branch of it, you're going to have a continuous function. And then the same is going to be hold true for, cotangent, secant, and cosecant. And then inverse trig functions as well. Now, as you remember, the domain of the inverse trig functions is restricted because of the fact that we need a one-to-one function. So on that small domain, though, everything is continuous. Also, exponential functions, right? That's very nice. Nothing's wrong with the exponential function. The domain is all real numbers. Of course, all the answers are positive. Our range is just positive numbers. Logarithms then being the inverse are also continuous, but their domain, of course, is all positive numbers. So all of these are continuous, which is great. You know why? Because now we can take the limits of all these with the theorem that I'm going to put on the board. So this is a little wordy, but it's not that hard to see. I'm trying to get my A's and my B's straight here. So this is how it's set up in your book. So this is equal to f of b. So that isn't very useful as too many A's and B's for my taste. So the way I like to remember it is limit as x goes to a of the composition f of g of x. Because f is a continuous function, I can pull the limit in. So, you can't do this unless this function is continuous at the point where this limit actually gets you to. That's why they have it stated in this way with the A's and the B's. But the idea is, as long as everything is continuous, you're good to go. So if I have a limit, so this is the direct substitution property that we first just talked about how it worked for polynomials and rational functions. But of course, you can actually do this for any continuous function. It has to be continuous at the point where you're trying to pull the limit in. All right? So if I have the limit as x goes to 3 of cosine of 2 pi x plus pi over 3, whatever, I don't know. Okay? I just made this up, but cosine, of course, is fine everywhere. So all I have to do is pull that guy in, and I end up with my direct substitution property, and I'll write this as a separate step. But quite honestly, you don't even have to write it as a separate step. I can just write this as 6 pi plus pi over 3, and you can actually figure out what that is, because the 6 pi doesn't change anything, right? So this is pi over 3, cosine of pi over 3 is 1/2. Right? Fine. Let me do another one real quick. So all you have to worry about is whether everything is defined nicely. And I will tell you in this particular section, it should be, because we haven't really talked about what to do if it's not, like if you end up with an infinity in there or something. We'll talk about that next week. For sure. Is the next section. Okay. So natural log of whatever, right? Well, what is the whatever? If I put in 1 in there, it looks like it's going to be fine. I'm not dividing by 0. I'm not getting a negative number. So this is going to be just fine to pull this guy in here. And again, you can do this step in your head. Just sort of do the substitution of 1 for x in your head to make sure that it's okay. You don't have to write it separate. And this is fine, right? This is natural log of 2/3. I couldn't do it if I ended up with something negative or something that was 0, right? Because those numbers aren't in the domain of natural log. But I can do it now because at 1, whatever this mess is, it's going to be continuous because I've got some continuous functions that are composed.